Okay, I have started recording and let's see. I have a couple announcements. First is that the first two, well, the second two out of three lectures are now available on YouTube. So I'll send a link out on Sakai to everyone. I haven't yet started uploading the photos of my lecture notes, but I'll do that this afternoon after this class. So essentially within an hour after office hours are done, you should have videos of the lectures and the photos of the lecture notes available to you. Are there any questions either on the kind of access to resources or other questions before I get started?
I do have one question.
Sure.
So on homework 3, I believe it is, there's one question that the Wiley software says that there's a problem with, and it says to ask you if you still want us to solve it. So do you still want us to solve it?
Nah, I'll check on that. I'll just not deal with that.
Sorry, did you say no?
Yeah. So I'll try to deal with that in whatever way I need to, but I don't think that it's worth our trouble struggling with a problem that might have more difficulties than just mathematical ones.
Okay, cool. Thank you.
Another important note, if people have started the homework 3, I turned off the require showing work. Has that translated into a better experience for people who have started working on homework 3?
Yeah, it has.
Okay. I am very interested to see your work on the midterms and on the final, but on the homework, I'm just hoping that you get the practice that you need on these problems.
Is the office hour also on the Zoom or something else?
Yes, the office hour is also in Zoom. Probably what will happen is I will just take a 5-minute break around 1 and then come back at 1:05 and then try to answer your questions. Yeah.
Is the
I'm sorry, I think my internet might have broken up, but I didn't quite understand what you said. Sorry, could you perhaps type your question? I'm not hearing you very well. Is the link the same? Yes, I'll be using the same number for the room, and I actually won't turn off the room. So if you want to just stay online, then I'll come back in 5 minutes. So there's no issue. Yep. Any last questions before we get started today? Okay. So let's begin with a review of what we were doing last time. So last time, 1 second. Okay, great. Last time, we essentially were solving the general solution to first order linear ODE via integrating factors. So we found the general solution to first order linear ODE via integrating factors. And I just want to kind of go through the process of an example again. Let's examine, so a linear first order ODE will look something like this. Y prime, or dy dt, is going to, we're going to have dy dt plus a of t, y of t, being equal to g of t, where g is some function. And so can someone remind me what the process of an integrating factor solution looks like? What am I trying to do with the left-hand side of the equation?
Make it into a dot product.
Yeah, exactly. I want to find some function mu of t, so find mu of t, such that when I multiply mu of t y prime plus mu of t a of t y of t is equal to mu of t g of t, such that the left-hand side looks like a product rule. So what is the differential equation that needs to be satisfied for the left-hand side to look like a product rule?
D mu of t dt equals to mu of t dot at.
Exactly. Mu of t times a of t. If I want this expression to look like a product rule, then here it looks like I took the derivative of the y term. Here it looks like I left the y term alone and took the derivative of mu and got back mu of t times a of t. And so once I solve this differential equation for mu and find any solution, then I can proceed by writing the left-hand side as an actual product rule. So let me do an example. And this, since it's Monday and since we're getting started back up again, I'm going to work out a part of this example, but then I would like for you to finish it. So let's try to solve the following initial value problem. I want to find a function y such that it solves this differential equation, ty prime plus t plus 1 y is equal to t. I want it to satisfy y of the natural log of 2 is equal to 1, and I want this to be valid where t is greater than 0. Okay? Any questions just on the setup? Okay, so what should I do to make this function look like the previous intermediate value solutions that, or the previous linear first order ODEs that we've solved?
Divide the whole thing by t.
Exactly, we should divide the whole thing by t, so we should get y prime plus t plus 1 over t, y being equal to 1. Here is where the assumption that y or t is greater than 0 is going to help us. And then we proceed. We need to find the correct integrating factor. So in particular, our integrating factor, mu of t, will be such that d over dt of mu of t is equal to t plus 1 over t, which is the same thing as 1 plus 1 over t. So why don't you, since I've gotten us started, why don't you find the solution to this intermediate value problem?
Can you scoot your paper down a little bit, please?
Oh, yeah, sorry. Unfortunately, my Zoom is not showing me in large screen what I've written, so I don't know how to fix that at the moment. So you might have to make that comment often today. Oh, I'm sorry. The differential equation should be satisfied is this one. The derivative of mu of t should be t plus 1 over t times mu of t. I'm sure that you all caught that before I did. So a quick question. Has anyone found an integrating factor yet?
Is it t to the t?
Yeah. So a valid integrating factor is mu of t is equal to te to the t. All right, how are we doing? Still need a minute or two? Sounds like yes. So maybe I'll just write down a couple more steps. If this is a valid integrating factor, then our differential equation can be written in the following form. Te to the t times y prime plus te to the t times t plus 1 over t y is equal to te to the t. And we recognize this left-hand side as a product rule, so we get d over dt of te to the ty is equal to t e to the t. Sorry, this should be. Did most of you get this far before I wrote it down? Yes, no,
Yeah.
Yes.
yes, I'm terribly wrong. So then integrating both sides, what I will get is that t e to the t times y is equal to t e to the t. Well, let me just write it as the antiderivative t e to the t dt plus c. What do I need to do to find the antiderivative of t e to the t?
Integration by parts.
Yeah, exactly. This is integration by parts. I want to, in some sense, move the derivative from the e to the t part to the t part. So what will I get if I perform the integration by parts?
You get t e to the t minus e to the t plus c.
Exactly. Thank you. This is integration by parts. And then I solve out to find the general solution, which is y is equal to 1 plus 1 over t plus c over t e to the t. And what's the last step that I need to do to solve the initial value problem?
Solve for C.
Yeah, I need to find what c is, right? And I need to use, I don't know if you can still see this, but I need to use the fact that y of natural log of 2 is equal to 1. So in other words, I'm going to set 1 being equal to 1 plus 1 over natural log of 2 plus c over natural log of 2 times e to the natural log of 2, so times 2, and we find that c has to be equal to 2. Wait, this should be a minus? I'm sorry, this is a minus, and this is a minus. So if c is equal to 2, these two factors will cancel out, and I'll get 1 is equal to 1. Did people get here before me? I hope so, but if not, that's fine too. So my final solution will be y of t is equal to 1 minus 1 over t plus 2 over t e to the t. Any last questions on this section where we're using integrating factors to solve linear first order ODEs? Is everyone bored? I need some response. Someone needs to say something.
I feel great.
Excellent. You feel great. We're going to move on. Happy to hear that. So next, we're going to move on to our first collection of nonlinear ODEs that we can attempt to solve. So now we're going to move on to 2.2 nonlinear ODEs, but a very special kind. As a kind of a preamble, I want to say that just like in so what do I want to say here? I want to say that the way that our calculus classes are normally taught and the way to kind of think about some of our integration rules is that the differentiation rules are usually relatively easy to find, right? We have a whole ton of differentiation rules. We have product rules, we have chain rules, we have quotient rules, we know how to do implicit differentiation. And then the strategy for integration was that for most of the easy integrations, what you did is you tried to undo one of the differentiations that you knew how to do. So for instance, you can think of the integration by parts as undoing the product rule or something like that. And then U substitution is the integration version of undoing the chain rule, right? So we think of integrations, or at least the elementary integrations, as undoing our familiar differentiation operations. So I want to remark that this first example of first order linear ODEs that we were able to solve essentially follows the same pattern. We multiplied by an integration factor in order to get the left-hand side looking like it was the image of a product rule. So we were kind of undoing the product rule in several variables, namely the variables y and t. And now we're going to do something that generally kind of looks like implicit differentiation. So I just want to remind you that let's say that we have, so this is kind of a prelude. Let's say that we have y is some function of x. Y is equal to g of x. And then let's say that we have some expression in terms of y's and x's. And for fun, let me just write them on different sides. So let's say that I have y cubed plus cosine squared, cosine squared of y is equal to 3x squared plus e to the x. When you learned implicit differentiation in Calculus 1, you learned that it's relatively easy to take the derivatives of this entire expression in terms of derivatives of x. Namely, if I want to take d over dx of both sides, so I want to set their derivatives to be, if this equation is equal, then their derivatives must be equal. So I can take the derivative with respect to x of y cubed plus cosine squared of y, and that'll be equal to d over dx of 3x squared plus e to the x, right? And the kind of rule for implicit differentiation is when you take, it's essentially chain rule. So I'm taking the derivative of this left-hand side. First, I'm going to take the derivative in y, and then I have to multiply by dy dx. That's what the chain rule tells us. So this left-hand side will be 3y squared plus 2 cosine y negative sine y. And then what do I need to multiply this whole thing by?
G prime of x?
G prime of x, exactly. I need to multiply this whole thing by dy over dx, which is equal to G prime of x. And then on the right-hand side, I'm just taking the normal derivative with respect to x. So I'll get this whole expression being equal to 6x plus e to the x. Is this familiar or comfortable?
Yeah.
This is a reasonable thing that I'm reminding you of. Essentially just chain rule, but maybe under the guise of implicit differentiation, because we can have x's and y's together. So the whole idea of the following class of differential equations that we can solve is that we can treat them like they're undoing this sort of operation. Okay, so a general, so now on to the actual content of section 2.2. So a general first order nonlinear ODE will look like this. It'll look like dy over dx is equal to some arbitrary function depending on both x and y. So for instance, as an example, I could write something like dy over dx is equal to e to the xy plus y cosine x. Just as an example of a general nonlinear first order ODE. Then what I can do is I can try to rewrite this as m of x comma y plus n of x comma y dy dx is equal to 0. Now, an obvious way that I can always rewrite something of this form like this is by taking m of xy to be negative f of xy and taking n of xy to be 1. But there might be other ways that I can rewrite this first order ODE in this format. So now we come to a definition.
Brian, can you confirm what the second half of that differential equation says after the e to the xy?
Here?
Yes.
I just wrote y cosine of x.
Okay, thank you.
As an example, but it's not particularly important. Okay, so definition. A first order ODE is called separable if we can write it as m of x plus n of y dy over dx being equal to 0. So for instance, this equation that I've written up here does not look separable because I don't think there's a good way to separate out this equation so that I have a function of x plus a function of y times dy dx. So here's a random general first order ODE that is probably not going to be separable, but we can find several examples which are separable, and I'll come to that pretty quickly. And the point is, separable ODEs can be solved directly by integrating. Both sides.
Can you move the paper down?
Oh, you mean up? Is that better?
Thank you.
By integrating, I won't say both sides. I'll just say directly by integrating. And the point is that if I rewrite this expression over here as n of y dy over dx being equal to negative m of x, then this looks exactly like this example that I did up here, which was kind of like implicit differentiation, right? If I have a function of y, right, this y cubed plus cosine squared of y was a function of y, and moreover, y is a function of x, and then on the other side I have a function of x, then when I take the derivative, I get something exactly of this form, a function of y times dy over dx being equal to some function of x. And how do I reverse this? That is, if I'm given something that looks like this, how do I find an expression of y, like an equation involving x and y, that when you take its derivative, it looks like this? Well, you just integrate both sides, right? So essentially, I'm undoing the process that took me from this equation to this equation. And I can always undo it if I have a separable differential equation that looks like this. So to explain a little more, by the chain rule, if y of x is a function of x, and I have, and then I take the derivative d over dx of, d over dx of f of y, then by the chain rule, this is going to be equal to f prime of y times dy over dx. And so this this piece is going to, I'm going to write this as f prime of y times dy dx, and this is just going to be m of x. So writing a little more, that should work. In other words, I'm going to have n of y dy over dx being equal to m of x. Well, I want to write this as being equal to g prime of x for some function g, and I want to write this as f prime, or d over dx of f of y for some function y. Or here I should write d over dx of g of x. And if I have d over dx of f of y being equal to d over dx of g of y, then I just take antiderivatives, and I'll be left with f of y being equal to g of x plus c. Will implicitly define solutions. So I've broken the first rule of talks, which is to give examples first, and then, if necessary, to prove theorems. Here, I've kind of discussed the theorem before doing an example. But I'll do.
Sorry, Mark.
Oh, yep.
Did you drop a negative sign? Like, wasn't it negative mx, or does that
Oh,
like
yeah,
not
you're right.
really matter?
It doesn't really matter, but you're right. I did drop a negative m
Okay.
of x. I just want to
But
write.
it doesn't affect, like, gx doesn't have to be negative, right?
Right. I'm just saying, like.
Yeah. Okay.
I'm just looking for some function whose derivative is this function as a function of x,
That makes
whatever it
sense.
is.
Okay.
Yeah. So I did drop the negative, but it doesn't matter for what I'm trying to explain. Okay, so any other questions before I go to an example? Okay, so the example I'm going to do is coming right out of the book for this first one so that you can look back on it or read the book's treatment. Let's try to solve, or at least find implicit solutions to, dy over dx is equal to x squared over 1 minus y squared. Now, there are kind of two ways to approach this, and they don't mean anything different mathematically. They're just different ways of writing it that you might see. One way is that I can certainly multiply both sides by 1 minus y squared and then subtract an x squared from both sides. So I can algebraically rewrite this as negative x squared plus 1 minus y squared dy over dx is equal to 0. Right? And now I have something of the form n of x plus n of y dy over dx is equal to 0. So this is a separable first order nonlinear differential equation. Why is it nonlinear?
Because of the square.
Yes, first of all, because I've got a y squared, and second of all, because I've actually got a y squared times dy over dx. So I'm doing two multiplications, neither of which would be allowed if I were doing a linear first order differential equation. Yeah, very good. Another thing that is often done when solving these separable first order differential equations is you'll see people treat this symbol, dy over dx, as though it can be split up. And so this, what I'll say is the following. This separable differential equation can be written in differential form as follows. This can be written as 1 minus y squared dy being equal to x squared dx, where essentially what I've done is I've treated this dy over dx, which should be treated as an entire symbol, right? This is the rate of change of y as a function of x, as though I can split it up into these two parts, which, if you remember, you might have spent like one day in Calc 1 on differentials, where you were writing out expressions like dy over dx. So a thorough treatment of differentials would be the reason why it is mathematically valid to split things up into this form. Now, either of these are going to give me the same answer when I take the antiderivative. Why don't I work with this one, with this expression? So I've got some function in terms of y, dy, being equal to some function in terms of x, dx, and the yoga of separable differential equations is that I can separately differentiate both sides and check that I get the correct solution. I'm going to integrate this side with respect to y, and I'm going to take the antiderivative of this side with respect to x. So what's the antiderivative of 1 minus y squared?
Y minus y cubed over 3
Yep. Y minus y cubed over 3
plus c.
plus c. Good. I'll put plus c1. This is going to be equal to, take the antiderivative over here in terms of x. X cubed over 3 plus c2. Since I get constants both times that I take antiderivatives, I can just move this c1 over here and forget that I had two constants. So I could just write this as y minus y cubed over 3 is equal to x cubed over 3 plus c. Okay? Any questions about this? Okay, and then the last thing to do is if we had an initial value problem that we were trying to solve, we'd solve for C. So what are we left with? We are left with the general solution of y. Let's move the x cubed over. So negative x cubed over 3 plus y minus y cubed over 3 being equal to C.
You skew your paper down.
Oh, yeah, sorry. Once again, I can't actually see what I'm writing very well, so sorry about this. It'll probably keep happening today, and I apologize. Okay, quick question. Is this a solution as we have previously understood it?
Not really.
Not really. What we usually want to understand as a solution is a function y of x being equal to some stuff in terms of x. This would be a general form of this would be what we would call an actual solution, such that when we take the derivative, it will yield back x squared over 1 minus y squared. The point is that this function right here this equation implicitly defines a function of y in terms of x. So this is kind of like writing down the equation for the circle, x squared plus y squared equals 1. This doesn't automatically give us a function which solves the particular equation, right? The graph of this equation is this circle, and if we want to actually find functions that solve this equation, then we're going to need to be looking at things like y is equal to plus or minus square root of 1 minus x squared, and then one of the solutions is going to be like the top piece of the circle, another one of the solutions is going to be the bottom piece of the circle. So the point is, when we arrive at this solution, it doesn't actually give us the explicit solution, but you know that locally this will define some function, and that the function that is defined locally by this expression will automatically satisfy this differential equation, which you check by doing implicit differentiation on this expression. So to check, we're going to say, assume that y can be written locally, and it's implicitly defined by this equation. Then if I take d over dx of this whole thing, negative x cubed over 3 plus y minus y cubed over 3, well, I'll take the derivative of both sides, equal to d over dx of c, some constant. Then what I get over here is I get negative 3x squared over 3 plus dy over dx minus 3y squared over 3, dy over dx is equal to 0. And then if I subtract over the x squared, I'll get dy over dx times 1 minus y squared is equal to x squared. And then if I divide back over, I'll get exactly the differential equation that I started with. So what I am doing here is I'm saying, if we have a separable differential equation, we can write it in these terms where we split up the function so that on one side I've got all of my expressions in terms of y, and on the other side I've got all of my expressions in terms of x. We take kind of naive antiderivatives. The result is this equation which implicitly defines a function y in terms of x, and then we check that whatever function this equation implicitly defines, it must actually satisfy this differential equation, because when we take derivatives, we're left with dy over dx is equal to x squared over 1 minus y. which is what we started with. Okay, kind of a complicated story, but it's really not so complicated in terms of the actual mechanics of finding equations out of separable differential equations, right? So any questions on this before we do another example? Not hearing any questions. Are we ready to move on to to another example of separable differential equations?
Yes.
Okay, great. So one thing that I want to point out, so a remark, is the following. Just as in the linear first order ODE, where we were dealing with integrating factors, it may not always be possible. Very nice, thank you, Madison. Just as in the linear first order ODE, it might not always be possible to write out my integrals explicitly. So remember, in the first order ODE, where we wrote down expressions like mu of t, d over dt, mu of t over mu of t is equal to p of t, mu of t. Oh, no, sorry, I already divided over. Is equal to p of t. And if you can actually integrate p of t in terms of elementary functions, well, then you're golden. You just do the integration. But in general, a general solution will look like mu of t is equal to e to the antiderivative from t0 to t of px dx. Remember how we were dealing with bothersome stuff like this? The same phenomenon appears in these separable nonlinear ODEs. So if we are able to write out something in terms of m of x dx plus n of y dy being equal to 0, it's possible that the best you can really do, so it's possible that the best you can do is write something like taking the antiderivative from x0 up to x of m of s ds plus the antiderivative from y0 all the way up to y n of, say, I don't know, I can also do s here, s ds being equal to c, right? So I'm just saying, all I'm saying here is that when you write out your separable differential equation, it's possible that you can't take a concrete antiderivative of m of x or n of y in terms of elementary functions, but you can always write this. And then by the first fundamental theorem of calculus, if I take the derivative of this with respect to x, I'll get back m of x. And if I take the derivative of this with respect to x, I'll end up with n of y times dy over dx being equal to 0. Okay, any questions on this? Ah, it's raining again. Okay, let me do another example because examples are wonderful. And I'm going to make you all do a bunch of examples because examples are wonderful. Oh, summer classes are great. So let's do the following example. Let's take, let's solve the IVP, which is given by x dx plus y e to the negative x dy is equal to 0, with the solution y of 0 is equal to 1. Okay, so what I'm going to do is the first thing I need to accomplish is I need to actually write this as a separable differential equation, which means I need whatever's in front of dx to only be a function of x, and I need whatever's in front of dy to only be a function of y. There's a very simple way that I can accomplish this. What's that?
Multiply by e to the x.
Yeah, exactly. I'm going to multiply everything by e to the x, so I can transform this differential equation into e to the x times x dx plus y dy is going to be equal to 0. And then now that I'm here, I can just integrate this component with respect to x and integrate this component with respect to y and be done with it. So what I'll get is the antiderivative of e to the x times x with respect to x is going to be, well, we already did this using the integration by parts. I'm going to get e to the x times x minus e to the x. So antiderivative of everything. It's going to give me e to the x times x minus e to the x plus y squared over 2 is equal to c. Any questions on what I did here? Once again, to check that this is going to implicitly define a solution which satisfies this differential equation, I just need to take implicit differentiation of this equation with respect to x. And I'll exactly get back to x plus y e to the negative x dy over dx is equal to 0. Okay, so this is the correct equation. And if I want y of 0 to be equal to 1, then that's the same thing as plugging in 0 for all my x's. So I get e to the 0 times 0 minus e to the 0 plus 1 squared over 2 is equal to c. So I get negative 1 plus 1/2 is equal to c. So I find that c has to be equal to negative 1/2. Am I right?
Yeah.
Yeah, I'm right. Great. And in this case, it turns out that I can actually write explicit solutions, more or less. So I end up with y squared being equal to, multiply everything by 2, I'm going to get negative 1 minus 2 e to the x times x minus 2 e to the x. So solutions to this differential equation could be given by y is equal to plus or minus square root of negative 1 minus 2 e to the x times x minus 2 e to the x, whenever this thing is positive. Argument is positive. Okay, so what I mean to show here, I suppose, is that despite all of the possibly confusing discussion that I gave beforehand, separable differential equations are simple to actually solve when you're actually going through it. You're just finding antiderivatives of both sides, one in terms of x and the other in terms of y. Any questions on this before I let you try one or two? All right, are you ready to try one or two?
Yeah.
Thank you. Man, I wish I could give out extra credit for people who talked. Anyways, you're getting extra credit where my mental health is concerned, so thank you. Let's do some examples. So why don't you solve, find solutions to the following two separable differential equations. First one being y prime plus y squared sine of x being equal to 0. And then why don't you do what would be good? Also do dy over dx is equal to y over x. So why don't you find the general form of solutions for these two separable nonlinear first order differential equations. I'll give you a couple minutes. Doing all right so far? Any questions right now? No?
No.
Okay, I'll let you keep at it for a couple more minutes then. So why don't we go over the first one at least? I can give you a couple more minutes to think about the second one. But what do I need to do to the first equation to write it as a separable differential equation?
Divide it by y squared.
Right, I can divide it by y squared as long as y is not the function 0. So what I'll write is two cases. one where y is not equal to 0. If y is not equal to the function 0, then I can divide by y squared on both sides, and I get y prime over y squared plus sine of x is equal to 0. And then this is now in separable form. If you want it to put into the differential form, then this would look like 1 over y squared dy being equal to negative sine of x dx. But these, I'm going to do the same operation. Doesn't matter whether I write it this way or this way. It's just a matter of taste. And then I just take antiderivative. So the antiderivative of 1 over y squared is negative 1 over y. And then the antiderivative of sine of x is negative cosine of x, I believe.
Where did the negative come from?
If I take the antiderivative of 1 over, or if I take the derivative of 1 over y, then I'll get negative 1 over y squared. Right, so maybe over here I can just kind of do a reminder that the antiderivative of 1 over y dy is equal to y squared is equal to negative 1 over y, and you just check by remembering that this is the same thing as negative y to the negative 1. And then when you take the derivative, the negatives will cancel, and you'll be left with y to the negative 2.
I meant like in front of the sign.
Oh, the antiderivative of sine is going to be negative cosine, right?
Right.
So minus cosine of x is equal to c. Are you happy with this?
Yeah.
Okay, sorry about that. I should have understood your question better before trying to answer it. Okay, and this will essentially define a function y in terms of x. If you actually want to solve out, you'll get something like negative 1 over y is equal to c plus cosine of x. And so y is equal to negative 1 over c plus cosine of x, if I did that right. Okay, so this is one family of solutions. Did everyone get this?
Yeah.
Yes.
Great, marvelous. Here's another thing that you have to remark. What about y equal to 0?
Then the solution would just be y equals to 0.
Yeah, this is also a solution. Also a solution. A much less interesting solution, but if I write y is equal to 0, then that will be a function y of x which solves this differential equation, so you shouldn't forget it. Okay, how about this one? How do I write this first as a separable differential equation?
You can just like divide by y.
Divide by y and then
over.
subtract 1 over x. So if y is not equal to 0, then I'm going to get negative 1 over x plus, am I doing this right? Plus, yeah, I'm doing this right so far. Plus 1 over y dy over dx being equal to 0. Did I do this one correctly?
Yeah, I think so.
Okay. So then what I should be able to do is I should be able to take antiderivatives of both sides. Why don't I multiply by a negative 1 just so that things are a little more... So essentially what I'll get is negative natural log of x, technically absolute value of x, plus natural log of absolute value of y is going to be equal to c. And if I take derivatives of both, if I take implicit differentiation of this, then I'll recover what I had here. And if I want to actually solve out let me just find one solution. If I wanted to solve all solutions, I'd have to go through the analysis of x and y, whether they're positive or negative. But here, what I should be able to do is put both sides as the exponent of e. So I should get e to the negative natural log of x plus natural log of y being equal to e to the c. And then simplifying this out, I should get, what's this going to be? Y over x is equal to e to the c, implying that y is equal to e to the c times x.
Could you move the paper up a little bit, please?
Oh, yeah, I'm sorry. Thank you. And of course, y is equal to 0 is also a solution. Sorry, if y is not equal to 0. Y equals 0 is also a solution away from x is equal to 0. So just remember that oftentimes y equaling 0 could be a solution to these differential equations, and you shouldn't forget it. But what I essentially want to go through here is the notion that separable equations are pretty easy to understand. As long as you can separate things out into function of x plus function of y times dy dx equaling 0 or equaling a constant or whatever, then you can integrate both sides and everything works out. Maxwell, yes?
Yeah, so I was just wondering, how do we know when to use like this method versus the method that we learned like the last couple of days, you know, where we just are like using like an integrating factor or something like that? Like how do we know which equations to use these methods for?
Yes, so the critical difference is that the previous methods only worked for first order linear differential equations. In other words, all of those equations I could write explicitly of this form. I could write them as dy over dx plus some function p of x times y is equal to g of x. This is a very explicit thing where I've got a 1 in front of the p of x, or dy dx. I've got some function only depending on x in front of the y, and then I'm having it to be equal to this g of x. This is a first order linear ODE. And this one we solved with integrating factors. These ones, this 2.2 stuff, is nonlinear.
Wait, could you scoot your paper down?
Oh, sorry. I really appreciate you all telling me this again and again, and I need to get my Zoom fixed so that I can see what's going on the screen. So nonlinear first order, separable. What I need to be able to tease out is I need to be able to tease out some expression that looks like m of x plus n of y dy over dx is equaling 0. Or actually, probably we can set it to be equal to another function of x. But if it were equal to some function of x, we just subtract that over and have a different m of x. So things of this shape. So for instance, something that looks like this, x cubed plus y cubed dy dx. This immediately is not a linear first order ODE because I'm multiplying my y's. First of all, my y's are multiplied together. And second of all, those y's are multiplying the dy over dx. So this is certainly not linear, but it's a nonlinear separable first order ODE. So we solve this version by separating variables. And maybe the separating variables is more clear if I write this as the y cubed dy being equal to negative x cubed dx. And now maybe it's more clear that what I've done is I've separated my variables on either side. Or if you don't like this differential form of it, you can always write y cubed dy over dx. I'm sorry, I'm writing off the page. Y cubed dy dx being equal to negative x cubed. This is another valid way of seeing that I have separated my variables into a nonlinear first order ODE. And these are solved by separation of variables. So that's a very good question. A kind of unfortunate, oh shoot, a kind of unfortunate part of this class is that it feels a little like integration, where we didn't get any big general rules for how to integrate things. It was just a lot of examples, like, oh, these specific kind of functions you can integrate, these specific functions you can integrate. It's going to be kind of similar for differential equations, where it's like, this special kind of equation, you can find a solution to the differential equation by using this special technique. And for this other special kind of differential equation, you can find solutions by using this other technique. So it feels kind of like piecemeal, like you kind of just have to memorize the different techniques for the different kinds of equations. Which, when I first took differential equations, I found kind of unsatisfactory, but that's life. Any further questions on this? No? No questions?
I had a question about your example from before.
Mm-hmm.
So can I write e to the c as another like arbitrary kind of constant, like another like b or c prime?
Absolutely. So a general form here would be y is equal to kx, where k is any constant. So depending on whether this constant is positive or negative should possibly come from a closer analysis of when x is negative, or when y is negative, or things like that.
Okay, thank you.
But yes, this would be the kind of most general form of the solution of these differential equations. Okay, so we're moving kind of quickly in this class. So essentially, unless you have further questions, this is all I'm going to say right now about separable first order nonlinear ordinary differential equations. And it's such a mouthful every time that we have to, like, when I have to say what kind of differential equation we're examining. No questions? Okay. What should I discuss next? I'm going to briefly tell you a little bit about modeling, but I don't know if I'm going to assign problems from 2.3. So 2.3 goes back into modeling. Real world problems. And it kind of returns us back to the world of first order linear differential equations. So I just want to kind of briefly mention some of the problems that we're now kind of comfortable with. One of them will be mixing problems. AKA pond or whatever, pond or reservoir with a certain amount of fluid coming in and the same amount of fluid coming out, and some pollutant or some amount of salt or something like that. So the reminder, just the reminder that I want to set up is that we set up differential equations for these mixing problems as follows. essentially, if you have, so let me just write up the examples that appear in the book really briefly. I don't want to take too much time, but let's say that we have at t is equal to 0, a tank contains Q0 of dissolved salt in 100 gallons of water. Gallons with 1L or 2? Probably 1, right? Gallons.
I think it's 2.
2 gallons of water. Let's say that water with 1/4 pound of salt per gallon flows in at rate R, and water flows out at the same rate. So the general setup to differential equations of this form is, if you're interested in the quantity of salt in the tank as a function of time, the way that the amount of salt is changing, so dq dt, is going to be the rate in minus the rate out. So we've already essentially done kind of simple versions of these problems at the very beginning of class or in your first homework. With this particular example, the rate in is going to be what? So the rate of the water coming in is R, and for each gallon that comes in, I get a 1/4 pound of salt. So I should have some function of R being my rate at which salt is coming in.
That'd just be 1/4 R.
Yeah, 1/4 R. Very good. This is my rate that salt is coming in. And then I need to subtract the rate that it's coming out. So the rate of water coming out of this thing is going to be R, once again, if I'm assuming that this tank is staying at the same amount of gallons at all points in time. And then what is the concentration of salt in the whole tank?
Q over 100.
Yeah, exactly, Q over 100. So in this way, we set up a nice linear first order differential equation. So I get dq dt plus rq over 100 is equal to 1/4 r. This is a nice linear first order ODE. And we solve this via integrating factors.
Please get down, please.
Oh, yep. What a disaster. Solve via integrating factors. Now, if we loop back around and remember that we now know how to solve actually much more complicated linear first order ODEs, I can set up a problem where, let's say the rate in, now I'm kind of stealing from another problem. Let's say that the rate in of water coming in is something like dependent on time. Like I set a fixed rate, R, and then I multiply by 2 plus sine of 2t. So in other words, in this setting, I am at certain points putting in water into the tank, and in certain other points, I'm taking out water of the tank. I can similarly, essentially what I'm saying is now we can deal with much more complicated rates of stuff coming in and out of the tank because we set up the exact same differential equation. Well, dq over dt is once again going to be the rate coming in minus the rate coming out. So let's say now I could write r times 2 plus sine of 2t over 4. say this is the rate of salt coming in, minus R times Q over 100. The point is that, once again, this is a first order linear ODE, dq over dt plus R over 100 Q is equal to some complicated function of t, R 2 plus sine of 2t over 4. And the point is, this is just as easily solvable as this previous one was, because it's just a linear first order ODE. And I can make things even more complicated by making the rate of water, or essentially the rate of salt flowing out, also depend on time. All those would lead to the same class of differential equation, which is a linear first order ODE. And another class of question that is brought up in this chapter 2.3, which I don't think I'll assign questions on, is questions about like interest rates. So for instance, let's say that you have some amount in the bank account. We'll say P of T is how many pounds you've got, because we're British. And so if you have some bank account which, say, compounds continuously, and also that you're constantly withdrawing small amounts from continuously, then we can easily set up a differential equation which models the growth of the number of pounds in your bank account, dp over dt. And once again, it's going to be equal to rate in minus rate out. So let's say that our rate in is going to be some, like, let's say 0.005 times the P of T. This is saying that we're continuously compounding the money in our bank account at a rate of 0.005, well, this would be like 0.5%, something like that. And then let's say that we're also continuously withdrawing some amount of money, which looks like negative, what's a reasonable function? Negative sine of t plus 2. So I'm always withdrawing some positive amount from my bank account, but it's sinusoidal times P of t. Then what I've once again done is I've set up a first order linear ODE, which, if I solve it, the solution will give me how the amount of money in my bank account is changing over time. So all that I want to point out here is that there are a large variety of physical interesting situations which can be modeled by linear first order ODEs. Any questions on this? No questions? Shall I move on then?
Sure.
Yes, please.
Great. So I've got 10 minutes left, and what I'm going to start discussing is the very interesting material of chapter 2.4. So 2.4, we're going to start looking at general questions. General questions about existence and uniqueness of solutions to, say, first order ODE. And since I don't have time to actually completely do this subject, I just want to make a couple remarks. So remark. The difference between linear and nonlinear ODEs will become very clear when we start looking at these very general theorems of existence and uniqueness. So linear ODE versus nonlinear ODE, these will behave differently. Why don't I just write down the theorems, and then I'll give a more thorough discussion of the theorems starting tomorrow. So here's theorem 2.4.1. This is existence and uniqueness for first order linear ODE. So the theorem goes as follows. If P of t and G of t are continuous, on an interval I, so I'll write it as alpha less than t less than beta, containing t0, then there exists a unique, is this visible? Then there exists a unique function, y, I'll write it as theta of t, satisfying y prime plus p of t y is equal to g of t, and satisfies the IVP of y of t0 is equal to y0. And it's satisfied on this whole interval. And this function is defined for alpha less than t less than beta. Okay, so a brief discussion of this theorem says for linear first order ODEs, as long as the functions p of t and g of t are continuous functions, then we are guaranteed both the existence of solutions and their uniqueness as long as we specify initial data. This should really come as no surprise because, first of all, we did a lot of examples with continuous functions p of t and g of t. And the critical thing to remember is that in its most general form, I was using integrating factors and I was writing expressions like mu of t is equal to e to the antiderivative t0 up to t of p of x dx. And I was writing things like mu of t times y is equal to the antiderivative from t0 up to t of something like mu of t g of t, or sorry, mu of x g of x dx, right? And so what this theorem will rely on is the fact that when p of x is a continuous function and when g of x is a continuous function, then these new functions that I define in this way, namely this way of defining a function via a definite integral, these satisfy the nice properties that we want, such that the derivative of this function is exactly equal to mu of x g of x, and the derivative of this function is exactly equal to, or mu of t p, g of t, and the derivative of this function is p of t. So what I want to say is the proof of this function will essentially be examining these expressions and looking at precisely what the first fundamental theorem of calculus says. The second thing that I want to point out is that this tells you essentially exactly how far you can extend the solution. That is, the solution is defined for all t such that p of t and g of t are continuous functions. So in the remaining, first of all, are there any questions? No questions? Everyone's comfortable with what I've written here?
Yes.
Great. Hey, that's really cool. So let me just do kind of a brief example. So let's find the interval in which the IVP has a unique solution. If my IVP looks like t minus 3 times y prime plus natural log of t y is equal to 2t, and y of 1 is going to be equal to 2. Okay, so what is the first thing that I should do? Well, I should first rewrite this into our standard form for first order linear ODEs. So what's that kind of standard form?
Y prime plus p of t y.
Exactly.
Something else.
And so to be explicit about that, what that means is I need to divide everywhere by t over t minus 3. So I'm going to get y prime plus natural log of t over t minus 3 times y is equal to 2t over t minus 3. Okay, so here's my function p of t and here's my function g of t. What is the domain on which p of t, this function, is continuous?
Can you move the paper up, please?
Oh, how's that?
Good, thank you.
So where is p of t continuous?
When t is not equals to 3.
Exactly. First of all, I need t to not be equal to 3, and I can't let t be negative, right? Because natural log of t isn't defined for negative t, right?
Yeah.
So p of t is continuous on the range or the domain 0 to 3 union 3 to infinity, right? I can't have anything negative, and I can't be at 3, but I can be in between 0 and 3 and between 3 and infinity, and both of those will make this function continuous. Any questions? Okay, where is g of t continuous?
Everywhere except t equals 3.
Exactly. G of t is continuous on the interval from negative infinity to 3, union 3 to infinity. What this is telling me is that the domains on which I can expect to have solutions are either between 0 and 3 or between 3 and infinity. Now, in which of these intervals does 1 lie?
0 to 3.
0 to 3, exactly. So t equaling 1 is inside 0 to 3. So what the theorem tells me, I'm sorry, I have totally run out of space, but I don't want to start on a new page. What this theorem tells me is there exists a unique function, y is equal to phi of t, defined on 0 is less than t is less than 3, such that y satisfies the IVP. Namely, the derivative of y satisfies this function, and y of 1 is equal to 2. So it tells me existence, uniqueness, and it tells me the domain on which this function is defined. And it can be taken to be the biggest domain on which my two functions are continuous functions.
Wait, what does that last line inside the box say?
Y satisfies the IVP, which means the derivative of y satisfies the differential equation, and I have some specified data. In this case, y of 1 is equal to 2. Remember, I can't expect uniqueness of solutions if I don't specify some additional data, because solutions to differential equations come in families. Okay, I'll go over this material again tomorrow, so don't worry if this feels a little unclear. And I'll also go over what happens in the nonlinear case. I'm gonna take a break for 5 minutes and then I'll come back for office hours. Thanks for bearing with me and going over by a minute or two.
Thank
Have
you.
a nice afternoon.
Thank
Thank
you.
you.
Thank you.
So long.
Thank you.
Oh, yeah. Oh, yeah, that one. Here, if you want to. Yeah, I'm muted right now. At least I think so, right? I'm muted? Good. Okay, yeah, if you come in. This is not bad. I am immune. Please. The thing is, this happened to us 2.5 years ago, and it was like dominant. Like, yeah, the last time it was right where Mark is, like, and it was like I had to sleep on the couch because I would like gag if I were over there. Well, it took us several days to figure out what it was, and eventually it's like, oh, it must be a dead animal. But like, I think we probably rolled like on day 6 before we got them to come out, because I think the first 4 days were like, what is this? So this is just like day 2. October, but it was like early October and it was still hot. They keep. Yeah, it gets worse as the day goes on, and because today's not bad heat, it's not as bad. Like yesterday was worse now than it is today. Yeah, so he just came over and he came in to figure out where to look. But it was bad last night at 2 a.m. before the rain started. Yeah. Yeah, it's here. This I think. But in the restroom, it smells a little. Yeah, and my room doesn't smell that bad. I've also kept the window open. So I gotta go back to that. I'm gonna be doing office hours now, so.